Hello, we are meeting again to discuss the application of statistics in management studies. I am Professor Venugopalan, retired from Sri Kerala College, Thrissur, under University of Calicut, now a faculty member at Dr. John Mattai Center for Management Studies, Thrissur, and Shaktan Tamburan College for Mathematics and Arts, Thrissur. Today we are discussing the applications of linear programming, the third part of transportation problem. Transportation problem is a branch of OR, operations research. It is application of linear programming, that is a problem of constrained optimization. Optimization in economics and commerce means either maximization or minimization. Constraints means restrictions. In transportation problem, the constraints are restrictions related to availability and requirement. That is demand and supply. Both demand and supply are finite. It cannot be changed by the decision maker. That is the problem. And objective is minimization of transportation cost, satisfying the availability and requirement conditions. So that's a problem of decision making. The decision maker has two stages of decision making. One is getting a solution satisfying demand supply and getting the minimum of transportation cost. In this class, I am going to discuss the optimization of a transportation problem. In the previous two classes, we discussed what is meant by transportation problem and the methods of getting an initial basic feasible solution. Today's objective is to derive an optimum solution, that is the minimization of total transportation cost, satisfying availability and requirement conditions. Once we get IBFS, then we go for distribution to modify such that the solution is optimum, the cost is minimum. Its method is known as modified distribution method, that is MODI. Today I am discussing MODI. After getting initial feasible solution, IBFS, we are moving to derive optimum solution. Optimum solution is a solution where the cost is minimum, satisfying demand and supply conditions. For that we use modified distribution method, shortly known as MODI. So for applying MODI, we have some requirements. What are they? A problem should be balanced. That is the condition for obtaining IBFS. That is the first and most important condition. A problem should be balanced. When it is balanced, that is the total demand is equal to supply. That is the condition for balanced problem. Second one is the solution obtained by an initial method. We have three different methods: northwest corner rule, lowest cost entry method, Vogel's approximation method, for obtaining an initial solution. That is a solution for satisfying demand and conditions. The cost need not be optimum or minimum. It is known as IBFS. A solution, that is the next condition. For going for MODI, the solution, the allocation should be m plus n minus 1, m plus n minus 1, where m is the number of rows, n is the number of columns. This condition is known as non-degeneracy. Non-degeneracy. This condition is required. If there is no m plus n minus 1 allocation, we cannot go for MODI. That point is to be noted. For obtaining MODI, this condition is okay, this condition is satisfied. Then there is a question. We have different methods by For obtaining IBFS, we can use any one, but it is the most suitable method is Vogel's approximation method. Why? It gives the solution nearest to optimum. If we use WAM for IBFS, the number of steps required for MODI is minimum. Otherwise, the procedure may be lengthy. Therefore, for obtaining IBFS, it is better to use Vogel's approximation method. After getting Vogel's approximation method solution, we have to consider whether it is a non-degenerate solution, then only we go for MODI. So what is MODI? Modified distribution of IBFS. Initial basic feasible solution is to be modified for what? To attain minimum cost of transportation cost, or there's a problem of linear programming, constraint optimization. The optimization means minimization of transportation cost, satisfying demand and requirement conditions. So that is again to less. What is the objective function? Minimize transportation cost by satisfying availability and requirement conditions. Then MODI has two stages. First obtain IBFS, then go for MODI to get an optimum solution. A transportation problem is given as origin, destination, etc. etc. These are so familiar to us. Supply 200, 160, 90, demand 180, 120, 150, and total is 450. So it is a balanced problem. That is the first condition. That should be balanced. It is satisfied. Then our first demand is obtain IBFS. We discussed in part 1 and part 2 the three methods, and it is better to use WAM. Then by WAM, Vogel's approximation method, IBFS is marked on the board. IBFS. You are so familiar with this procedure, so I am not illustrating the Vogel's approximation method in this class. It is known to you. So this is the initial basic feasible solution for this problem. The entries in red are the allocations. 16 is the cost. 16, 140 is the allocation. Then look for this total. 140 plus 60, 200. 40 plus 120, 160, 90. 140 plus 120 plus 60 plus 90, etc. This is an initial basic feasible solution. How many allocations? 1, 2, 3, 4, 5. 5. That is m plus n minus 1 equal to 3 rows, 3 columns, 3 plus 3 minus 1 equal to 5. There are 5 allocations. There is the condition for going to MODI. So this problem is ready to apply MODI. This is an initial basic feasible solution. It is also known as non-degenerate, since m plus n minus 1 is equal to 5. This is a solution of IBFS, non-degenerate, ready to apply MODI. Then as usual, we calculate the total cost. Now we are familiar with the two words, optimum and total. This is only a cost satisfying availability requirement. Why we use WAM? WAM gives the next to optimum. For finding initial basic feasible solution, if you use WAM, the number of steps in MODI is minimum. That is the most important point to be considered by a student of the initial stage. Therefore, then the total cost is equal to 16 into 140 plus 12 into 160, 14 into 140, 14 into 40 plus 8 into 120 plus 6 into 90. That is the total cost. That is rupees 5920. One more thing. There are 1, 2, 3, 4, 5 allocation cells. In the other cells, the cost coefficients are not written now. That is, we have two types of cells. These cells are called allocated cells, allocated, and other cells are non-allocated. In MODI, our interest lies in both, which are the allocated, which are the non-allocated. So we have two new words, allocated cells where the allocations is done and the non-allocated cells where the allocations is not allowed for the type being. This is the initial basic feasible solution by VAM. We are going to derive optimum solution by using the method MODI. MODI method is also known as UV method. That is a procedure. This is the initial solution 140, 60, 200, 40, 120, 160, 90, 180, 120, 90, 1, 2, 3, 4, 5 allocations. 3 plus 3, 6 minus 1, 5 allocation, non-degenerate basic feasible solution, just discussed earlier. Then, there are two types of cells. One is allocated cells, allocated. What are they? This is an allocated cell. Here the allocation is an allocated. 5 cells are allocated. That is, from origin 1 to destination D1, 140 units are transported with a cost of 16 per unit. This is a solution and this is the allocated cells. And there are the remaining cells. They are called non-allocated cell, non-allocated. Then this MODI method is also known as UV method. That is known as UV method, UV, where U and V are two arbitrary constants, U, students, V, the teacher may be explained as like that, U and V. Teacher and students are going in association for solving a solution, UV method. What is U? As the arbitrary constant. V, an arbitrary constant. And we are going to derive or state a relationship. C is equal to U plus V. C equal to U plus V, where C is the cost. And we calculate two coefficients such that C for allocated cells. That is simply a puzzle. What is C? Cost. What is U and V? They are two constants. For what cells we calculate? Allocated cells. We calculate U and V for allocated cells by an arbitrary method. Then starting for that procedure, that allocation, we use U and V method, U C equal to U plus V at first for the allocated cells. That is, for allocated cells, we U for column, row, and V for U for row and V for column. Let's starting U here, V here. The first row we calculate U1, U2, U3. Here V1, V2, V3. That is for allocated cells. Yes, starting with allocated cells. There are two allocations. One allocation in the row, column, two allocation, one allocation, two allocation. Start with an arbitrary allocation. For convenience, I assign U1 equal to 0. That's an arbitrary. You can assign anything. For simplicity, I assign 0. For the first row, why you take first row? There are two allocations. It is better to allocate arbitrary a 0 for the row or column having the largest number of allocations. Then C is equal to U plus V using this method. Here, that is for C, the first cell, it is 16. V1 plus 0 is equal to 16. So what about V1? V1 is equal to 16. 16 is equal to 0 plus 16. So here we get V1 as 16. V1 is equal to 16. Very important state. Listen carefully and observe carefully. Then for U2, how will you calculate U2? Here it is 14 something. U2 plus V1 is equal to 16. Therefore, U2 equal to 16. 14 minus 16 is equal to U2. So, U2 is equal to minus 2, minus 2. Using this relationship, we go for U3, etc. Using allocated, that's the most important point. Using allocated, here it is cost 8. 8 is equal to U1 plus U2, U2 plus V2. U2 is 8 is equal to minus 2 plus V2. Therefore, V2 is equal to 8 plus 2. 8 plus 2 equal to V2. V2 is 10. V2 is 10. Then V3 is equal to 0 plus 12. So V3 is 12. V3 is 12. That is, V3 is, what is U3? Something is totally 16. 12 plus something. 12 plus something is 16. 16 is equal to 12 plus U3. 12 plus U3. Therefore, U3 is 16 minus 12. 4. So, all coefficients are determined for the using the cost coefficients of the allocated cells. U1 is 0. U2 is minus 2. U3 is 4. V1 is 16. V2 is 10. V3 is 12. So, this method is known as UV method, the modified distribution. This is only a check whether the distribution is optimum or not. Then, now we are moving to the non-allocated cells. 20, 18, 26, 24, non-allocated cells. Using these arbitrary coefficients of U and V, we calculate another method, that is a coefficient like C minus U plus V. C minus U plus V for non-allocated. Let us go for that. Here it is 20 minus 10 plus 0. 20 minus 10 plus 0. 20 minus 10 plus 0. That is 20 minus 10. It is 10. That is allocated here. That's a test. 10. Then here 18. 12 minus 2. That is 18 minus 12 plus minus 2. 18 minus 12 minus 12 minus 2. That is 10. 18 minus 10. 8 here. 8. Here 16 minus 2. 14. Here it is 26. 16 plus 4, 20. It is 6. 10 plus 4, 14. 24. It is 10. That is, for all non-allocated cells, the test coefficient, this is a test coefficient test for non-allocated cells are positive. That is the test for MODI. If in the non-allocation cells, if this test dose are positive, the solution is optimum. Therefore, by MODI method, this solution is optimum. No modified distribution is required. The derivation or allocation obtained by VA is optimum. MODI is only a check for, nothing to modify in this problem. So, this problem gives the same allocation obtained by VA as the modified distribution or the optimum solution. Then we find the optimum cost. The optimum cost is same as derived in the initial basic feasible solution. It is, what is the optimum cost derived in that case? It is 40, 16 into 140. That is the difference is, it is the optimum cost. Optimum cost is equal to this. What is optimum? It is the minimum cost. Optimum is the minimum cost. It is 16 into 140 plus 20 into 12 into 60 plus 14 into 40 plus 8 into 120 plus 16 into 90, 1, 2, 3, 4, 5 allocations. It is rupees 5920. Rupees 5920. This is the Modi method. It implies that the distribution or the allocation obtained by BOM is equivalent to optimum. In the other way, if you find in this problem, if you use northwest corner rule for IBFS, it will take 2 or more 3 additional steps. So it is better to use BOM. Once again, I am concluding about Modi. We have 2 steps for allocation cells. Find C is equal to U plus V, where C is known in the allocation cells. U and V are 2 arbitrary constants. 1. U or V is designed arbitrarily. It is better to assign 0 for the most allocated row or column than find using C. Then next, after attaining U, V values for row and column, then go for non-allocated cells. If all that entries are positive, the solution is optimum. Otherwise, we have to go for Modi. Now I am reaching to the culmination stage of this class. Today we discussed modified distribution, and I discussed a simple direct problem. That is, the initial basic feasible solution is the optimum itself. One more class is required. In that class, we discuss a problem which requires modification. So, a problem of modification or optimum may be a lengthy problem. At the first stage, you should be confident about IBFS and obtaining IBFS by Vogel's approximation method. Modi step is not so simple, not any mathematical complication, any mathematical computation, but it requires a long steps, 1, 2, 3 or more steps, and you should be confident, and the numerical computation should be perfect. Otherwise, the steps may be deviate. Thank you for listening this class.